Bismillahirrahmanirrahim. Honorable speakers, all colleagues in Algebra Research Group of ITB, and all the participants online and offline. Um, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Um, Welcome to the Algebra Seminar Series organized by the Algebra Research Group of the Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. I'm Respi Taulan from Algebra Research Group of ITB, will be the MC of today's seminar. Um, First, I would like to thank our distinguished speakers, Professor Ahmad Erfanian and also Dr. Afsaneh Shamsaki from Ferdowsi University of Mashhad, Iran, for your willingness to give insightful discussion and also valuable perspective on the intricate world of algebra. And I would also like to thank all the participants who are attending this seminar. And I hope this seminar will give a lot of benefits for all of us. For the next agenda is a brief welcoming speech from Professor Mutadi Intan Detiana on behalf of the head of Algebra Research Group of ITB. So, Professor Intan, yours.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Thank you for coming to this algebra seminar series, our algebra research group, and we are gladly happy that we have offline speakers from Ferdowsi University of Mashhad, Iran, and Professor Ahmad Erfanian will be here for 3 days, and Dr. Afsaneh Samsaki will be here for 1 month. And you are welcome to have any discussion with them. And as for today, we will see their presentation about Lie algebra and also a graph from Lie algebra. Okay, so that's all I can say. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Professor Intan. So the next agenda will be our main agenda. But before, let me inform you our rundown for today. So we will divide our seminar today into two sessions. The first session is from 1:15 to 2 p.m. And it will be the presentation and also the Q&A session with Dr. Afsaneh with the topic of Introduction to the Algebra. And then we will have a 15 minutes coffee break. And then we'll be followed by the next session, the presentation, and also the Q&A with the topic on commuting of graph of Lie algebra. Okay, so before we start the first session, let me share a brief curriculum vitae of our first speaker. So her name is Afsaneh Shamsaki. She had her PhD graduated in 2021 in pure mathematics, algebra, and group theory and Lie theory of Faculty of Mathematical Science in Damgan University of Damgan, Iran, with the PhD title of On the Dimension of the Shear Multiplier of Nilpotent Lie algebras and Order of Finite P groups. Her main research interests are Lie algebras and group theories, also other topics such as Lie superalgebras, dissociative algebras, and the community degree of groups and graph theory. For her recent publication is on the topic of characterization and also classification of nilpotent Lie algebra. Okay, so without further ado, I invite Dr. Afsaneh to present your topic. So please, Dr. Afsaneh, the time is yours.
Hello, everyone. First of all, I'd like to thank Professor Intan for providing this opportunity. for me and Professor Ahmad. I'm glad to be able to present for you. Let me briefly introduce myself. My name is Afsana Shamsaki. I'm as a junior researcher and an advisor, Master of and PhD students at Ferdowsi University of Mashhad. I'm very enthusiastic Lie algebra, Lie super Lie algebra, and graph theory. I talk. I'm here to talk about like, some probabilities and graph associated to Lie algebra. Please show my screen. Page 2, please. Next page. My talk is divided 5 parts. I'll start with introduction of Lie algebra, and then we'll be learning about its relation with other branches of mathematics, such as probability theory and graph theory. And the final, I talk about our projects at ITB. I'd like to talk about general information about Lie algebra. Lie algebra are one of the algebraic structure. They have appeared application in other science, such as physics, especially quantum physics. There exist similarities between Lie theory and group theory, but they are not perfect most of the time. It seems that we can just use them for guessing some result in Lie theory. So having enough information and mastering group theory is necessary to understand the algebras. Next page. This table shows that some definition in Lie algebra are parallel to some definition in group theory. For example, subalgebra and ideal are parallel to subgroup and normal group in group theory, respectively. Also, some concepts in Lie algebra are the same concepts in group theory. For example, nilpotency, isocliness, and capability. But there are differences between definition in Lie algebra and group theory. For example, conjugate class has not defined in Lie theory, but and action of two Lie algebra, tensor product, and exterior product how difference definition in Lie algebra and group theory. For defining a Lie algebra, for defining
I want to tell you that okay. Yes, very Yeah, exactly. But I said
for defining a Lie algebra, we need to recall some definitions. For example, vector space, characteristic of a field, and bilinear map. Turning our attention in vector space. A vector space V over the field F is a non-empty set whose elements are called vectors with two different operations, addition and scalar multiplication, satisfying in the following properties for every vectors U, V, and W, and the scalar C and D. The next, the first operation is action. It obeys 5 rules: closure under addition, commutative property, associate property, additive identity, and additive inverse. This action makes an abelian group. And the second operation is scalar multiplication. Also, it obeys 5 other rules: closure under scalar multiplication, distributive properties, associate probability, and scalar identity. Characteristic of a field. Let F be a field. The characteristic of a field is the smallest positive integer n, such that if you add multiplication identity at itself, get 0, where 1 is the multiplication identity of L. If no such an n exists, we define the characteristic to be 0. For example, the characteristic of fields, rational number, real numbers, and complex numbers are 0. And the characteristic of finite fields, that P is P for any prime P. Bilinear map. Let V a vector space over the field F. Then F from V cross V from to V is a bilinear map if and only if following condition, these conditions, hold for all vectors A, B, and C vectors, and the scalar lambda holds for F. Let's now turn to concepts of Lie algebra. What is a Lie algebra? A Lie algebra over the field F is a F vector space L with a bilinear map from L cross L to L by sending the pair of X and Y to X bracket Y, called a Lie bracket, satisfying the couple of properties. The first property is as alternative. It means that X bracket with itself is 0 for all X in L. And the second condition is Jacobi identity. It says us X bracket with Y bracket Z plus Z bracket X bracket Y plus Y bracket with Z bracket X plus is 0 for all X, Y, and Z in L. Let me elaborate further on proposition of Lie bracket. I want to show this equation. We know that every element bracket with itself is 0. So X plus Y bracket X plus Y is 0. On the other hand, this bracket, the Lie bracket is bilinear. So this bracket is equal to this part. Again, by this fact, every element bracket x with itself is 0. This bracket, x bracket y, and this bracket, y bracket y, is 0. So x bracket y plus y bracket x is equal to 0, and we have the equation 3. If the field does not have characteristic 2, by putting x and y the same in the equation 3, shows that the 3 implies that alternativity. By a similar way, you can see that x bracket 0 is 0 for all x in L. The definition of Lie algebra leads me to this example. An elementary example for a Lie algebra is a vector space. Every vector space V is a Lie algebra with this operation. X bracket y is 0 for all x and y in V. This is the abelian structure on V. In particular, the field F may be considered as a one-dimensional abelian Lie algebra. The second example, general linear is the vector space for all n cross n matrices over the field F with this Lie bracket. X bracket y is equal to x product y minus y product x for all matrix x and y in general linear algebra, where x product y is the usual product of matrices x and y. And the second example, recall the trace of a square matrices is the sum of its diagonal interests. Let a special linear algebra be the subspace of general linear consisting of matrices of trace 0. For arbitrary square matrices x and y, this matrix x product y minus y product x has a trace 0. So this bracket define a Lie algebra structure on a special linear algebra. Also, the properties of Lie algebra are inherited from the general linear algebra. Next page, please. As I said at the beginning, subalgebra and ideal in Lie theory are parallel to subgroup and normal subgroup in group theory. A Lie subalgebra of L is a vector space L such that it is closed under the defined operation. We can see that Lie subalgebra are Lie algebra in their own right. An ideal of a Lie algebra L is a subspace I of L such that x bracket y in I for all x in L and y in I. By using this equation, so we don't need to distinguish between left and right ideals. You can see an example for general linear algebra. First, recall a matrix is said to be upper triangle if xij is 0 for I strictly greater than j. Let be the upper triangle matrices in general linear algebra. This is a Lie algebra with the same bracket, general linear. One can check that upper triangle matrices is a subalgebra of general linear algebra. Before stating relation between subalgebra, before stating relation between subalgebra and ideal, I recall this kind of matrix. The matrix Ij is a n cross n matrix which has a 1 in the Ij's position and all other integers are 0. An ideal is always a subalgebra, but its converse is not true. For example, consider upper triangle matrices is a subalgebra of general linear, but it is not an ideal provided n is equal or greater than 2. To see this, note that E11 is belong to upper triangle matrices, and this matrix is belong to general linear algebra. However, this bracket is not belong to upper bilinear matrices. The center of L. Before that, I recall some ideals. The Lie algebra L is an ideal for itself. Also, 0 is an ideal of L. This kind of ideals are called trivial ideal. An important example of an ideal which frequently non-trivial is center of L, defined by this the set of elements of L like X such that X bracket Y is 0 for all Y in L. And we have if L is equal to its center, if and only if L is abelian. In the next part, I introduce the centralizer of an element X and its relation with an linear map. The centralizer of a X in L is defined by this, the set of elements of L like Y such that X bracket Y is 0. By considering adjoint X, this linear map from L to L, by this rule, by sending L to X bracket Y, we have its kernel, it's the centralizer of elements X in L. The product of ideals. Let I and J be two ideals of L. The product of ideals is defined as follows. I bracket J generates by X bracket Y such that X in I and Y in J. And in a special case, the derivative subalgebra of L can be defined by putting I, J, and L are equal to each other. It is common to be denoted by L square instead of L bracket L. One important class of Lie algebra is Heisenberg Lie algebra. A Lie algebra L is called Heisenberg Lie algebra if its derivative subalgebra is equal to its center, and the dimension of the derivative subalgebra is 1. It is proved such Lie algebra or odd dimension and how this presentation. And quotient Lie algebra. If I is an ideal of the Lie algebra N, then I is in particular a subspace of L, and so we consider these cosets for all Z in L. And the quotient, and we have this quotient vector space. If this space equivalent to this Lie bracket, we have the quotient. We have a quotient Lie algebra and homomorphism and example for it. If L1 and L2 are to Lie algebra over a field F, then we say that a map from L1 to L2 is homomorphism if we have two conditions. The first condition is a linear map, and the second condition, the image of X bracket Y under phi is equal to the image of X under F bracket V, the image of Y under phi for are equal to each other for all X and Y in L. Note that in this equation, the first Lie bracket is taken in L1 and the second Lie bracket is taken in L2. We say that phi is an isomorphism if phi is also bijective. We have a good example for homomorphism Lie algebra. Consider F from L to quotient L by I, which takes an element, for example, Z to its coset. Is a homomorphism of Lie algebra because obviously F is linear, and It is enough to show how the second condition. By the rule of F, we have this part, and by the defined Lie bracket on quotient L by I, we have this part, and again by the rule of F, we have this equality. So the second condition holds for it. Isomorphism theorems in Lie theory are parallel to isomorphism theorems in group theory. The first isomorphism theorem, let phi from L1 to L2 be a homomorphism of Lie algebras, then the curve phi is an ideal of L1 and the image phi is a subalgebra of L2, and we have this isomorphism. The second isomorphism theorem, if I and J are ideals of a Lie algebra, then we have this isomorphism. These theorems are exactly isomorphism theorem in group theory. And the third theorems, suppose I and J are ideals of a Lie algebra such that J consists of I. Then the quotient J by I is an ideal of the quotient L by I, and we have this isomorphism. Let's now turn on the classification of nilpotent Lie algebra. Before that, I recall the definition of nilpotent Lie algebra and lower central series. Lower central series of a Lie algebra L, to be serious with this term, L power 1 is L square, and L power k is equal to L bracket L power k minus 1 for all k greater than 2. And we have this descending series. As the product of ideals is an ideal and L power k is even an ideal of L and not just an ideal of L power k minus 1. The reason for the name central series comes from this quotient Lie algebra is contained in the center of the quotient Lie algebra L by L power k plus 1. If this descending series stopped, L is nilpotent Lie algebra. More precisely, the Lie algebra L is said to be nilpotent if for some m equal or greater than 1, we have L power m is 0. A full classification of nilpotent Lie algebra of dimension at most 6 over an arbitrary field has been obtained by graph. You can see some presentation of them in the following, this presentation. Also, me and others classify nilpotent Lie algebra of class 3 with one-dimensional center and three-dimensional derived subalgebra. Let me go back what I said earlier about relation between Lie algebra and other branches of mathematics, such as probability theory. The commutativity degree for finite group defined, and we defined this definition for a finite dimensional Lie algebra over finite field like this, and observe similar and different results for them. Next page. First, I like to talk about these different results. Let the group G be a finite group. It is showed the commutative degree of this group is equal to the number of conjugate class of G divided by the order of G. But conjugate class have not defined in Lie algebra. And we prove that for a Lie algebra, the commutative degree is equal to these values. Let's prove that all groups with the commutative degree strictly greater than 1/2 are nilpotent. But we determine the existence of a non-abelian Lie algebra L with its commutative degree strictly greater than 1/Q, which shows that the above fact does not hold for Lie algebra. Also, Lescott showed if a group G has this property, then its commutative degree is 1/2. But we prove that there is no Lie algebra such that its commutative degree is equal to 1/Q. In this screen, our results is the same in group theory and Lie algebra. Two isoclinic Lie algebra or groups such that L and M have the same commutative degree. And we give upper and lower bounds for the commutative degree of a Lie algebra based on Q. As a result, we have a upper bound 5/8 for Lie algebra, similar to upper and lower bound obtained for commutative degree in groups. And other similarity between group theory and Lie algebra. Let L be a Lie algebra. Then the dimension of a quotient L by its center is 2 if and only if its commutative degree is equal to Q square plus Q minus 1 over Q power 3. Also, it is true for groups. Until this part, we've looked at introduction of Lie algebra and its relation with probability theory. Now I recall some concepts of graph theory and introduce some graphs associated to Lie algebra. A graph G consists of a pair VG and EG where VG is a non-empty finite set whose elements are called points or vertices, and EG is another part of the pair of has distinct others VG. The elements of EG are called lines or edge of graph. If E is the set of U and V, then line or edge. E is said to join the points U and V. And the vertex U and V are set to adjacent together by the edge of E. The non-commuting graph defined for a group. Let G be a non-abelian group and the G be the center of G. Associate graph to G with G as follows. Take G minus its center as the vertices of this graph, and two distinct vertices X and Y are adjacent together if they don't commute with each other. This graph is called non-commuting graph of G. Some properties of this kind of graph are studied. For instance, connecting, Hamiltonian, regularity, planarity, and outer planarity. We define this kind of group for Lie algebra. Let L be a Lie algebra and ZL be its center. We define associate a graph GL. Take L minus its center, the vertices of this kind of graph, and join two distinct vertices X and Y whenever X bracket Y is not 0. Let me use the explain this kind of graph. This graph shows off the element of L minus its center is 3 and X bracket Y and Y bracket X plus Y and X plus Y bracket X is not 0. And the second graph says us the elements of L minus its center is 6. Consider the vertex x. The vertex is adjacent the vertex y, x plus y, y plus z, and x plus y plus z. And we conclude the bracket x with this vertex set is not 0, but x is not adjacent to vertex x plus z. So we have x bracket x plus z is 0. We prove the next theorems, and it is a useful tool for obtaining the number of edge of the non-commuting graph, and it makes a relation among Lie algebra, graph theory, and probability theory. Let L be a finite dimensional Lie algebra over a finite field. Then the number of edge the non-commuting graph is equal to the order of L power 2 product 1 minus the commutative degree over 2. As I said at the beginning, we have our project with Professor Inhan and Professor Ahmad at ITB. We define G non-commuting graph as follows. L be a finite dimensional Lie algebra over a finite field, and G a fixed element of field. We denote the G non-commuting graph of L by this symbol as the graph with vertex set L and two distinct vertex x and y joined by a h if x bracket y is not equal to j minus g. Also, we obtain some its properties. In addition, we are going to do following classification. Classify all kind-free G non-commuting graph L when n equal or smaller than 5. Classify all G non-commuting graph L when this kind of graph has a vertex with degree of n such that n equal or smaller than 6. Classifier of planarity G non-commuting graph, and classify R regularity G non-commuting graph L when R smaller or equal than 15. I use these references in my talk. These references. Thanks for your attention. If you have any question, please ask me.
Okay, thank you for Dr. Afsane for your presentation. There's such an insightful topic for all of us. So now we have Q&A session. Maybe the participants in this room would like to ask Dr. Afsane? Or any participants in Zoom? Any questions?
Have you ever considered its relation with the Lie groups?
If relation in the Lie groups and probability theories. Yes, yes. Oh, okay. Okay, okay. Okay. So we have some facts for the algebras, but most of the time are different with the group. And we use group theory just for guessing. Just this. No, no. Mm. Uh, in fact, Lie algebra is a special case of Lie group.
Okay, so any other question?
Oh God. The first example. General linear. General linear is equipped Lie bracket. Yeah. I think that page 5. Oh, 10, 10, 10, 10, yes. Oh, next page. Oh, this. General linear equipped these Lie brackets. Okay? Okay. Special. Next page, next page. Oh, this. Zero.
Okay, any other question from Zoom participants, maybe? Okay. So any question from the participants here? Oh, we have one question from Zoom. Okay, this is from Muhammad Hassan Mudabir from he said, thank you for the presentation. What are the needs of associating a non-commuting graph to Lie algebra? What are the needs of associating a non-commuting graph to Lie algebra?
Exactly. uh, they said how we can say about the associativity. Is that important for the algebra?
Yeah.
Associativity. We should have so the algebra that you consider is associativity. So the really I think we always need for for this part actually defining a graph and probability, we may not need any extra condition like associativity. But maybe we can, if we have to consider some more specific cases, maybe associativity is important. For this part, this is not necessary, associativity.
Thank you, Professor. Is there still another question from Zoom? No. Okay, there's only one question from Zoom participants. Is there any more question from here? Okay. So, again, thank you to Dr. Afsane for your presentation. And let's all give her a round of applause. Okay, so now we will have 15-minute coffee breaks and we will be back at 2:15 p.m. Okay, so thank you everyone. Enjoy your coffee break. Okay, participants, if you would please back to your seat since we will start our next session. Okay, so the next session will be a presentation and also Q&A session with Professor Ahmad Irfanian. But before we start the next session, I would share some a very brief curriculum of our speaker. So the name is Professor Ahmad Irfanian. He gets his PhD in 1995 in pure mathematics, algebra, group theory in Cardiff University, UK. And his research interests are growth sequence of groups, combinatorial group theory, probability group theory, Sir multiplier, and isoclinism of groups. Also finite simple groups, graphs associated to groups and rings, and graph theory and combinatorics. He has wrote several books in Persian and English, also hundreds of scientific papers, and he was also awarded as Distinguished Full Professor by Minister of Science, Research and Technology and Vice Chancellor of Ferdowsi University of Mashhad in 2022. Right now, he acts as the head of international office at Faculty of Mathematical Science, Ferdowsi University of Mashhad, Iran, since 2022. So without further ado, I invite Professor Ahmad to present. So Professor Ahmad, if you please, the time is yours.
Very much. Okay, thank you very much, everybody. Good afternoon. Assalamu alaikum wa rahmatullahi wa barakatuh. First of all, I would like to thank Prof. Intan and also Prof. Butchi, Rawati, Editary, and many of colleagues here for providing this opportunity for me to have a few days here, only 3 days, of course. And will be here for 1 month. So I'm so glad that we have some collaborations from many, just I think from 5 big TC, about 4 years ago. And now we increase our collaboration to some of my graduate students. So I think every year I will send 1 or 2 my graduate PhD student here. And so they have some joint work with Prof. Intan, Prof. Butchi, Prof. Eddie, and I'm hoping that to continue this sort of collaboration with all of you, in particular a student of Prof. Irawati about relation between cryptography and graph theory and maybe probability. So what I would like to mention here is about one of oldest algebraic graph. So if somebody asks you, we have many algebraic graphs, what's the oldest one? The oldest one is Cayley graph. Because Cayley graph introduced it many, many years ago. It's something like 1951, 52 by Arthur Cayley. So it's very, very old Cayley algebraic graph. Now, what I would like to mention here is to, first of all, introduce Cayley graph and then some new graphs related to Cayley graph. Of course, some of them may be a generalization of Cayley graph or some other kind of Cayley graphs. So let me just in few minutes remind you about definition of Cayley graph. I know most of you know about the definition of Cayley graph. So if you take Cayley graph, for Cayley graph, we have a group G, right? And we have a subset S of a group G. We should have 2 conditions for subset S. Why we should have 2 conditions? Because we are talking about simple graph. Simple graph means that we don't have any loop. Loop means that a vertex adjacent to itself and any multiple edges. So for having this situation, we must remove identity from the subset S, because if we have identity, we may have a loop. And also because we don't like to have a uh, direction. So we consider the S inverse is subset of S. It means that if you take any element inside of S, the inverse, because they all belong to a group, we have inverse in a group. So the inverse of that element must be again in S. So with these two conditions, we can define a simple undirected Cayley graph, because we have some sort of Cayley graphs with direction, with multiple edges, and also even with loop. So the Cayley which I would like to consider here is the Cayley graph without any multiple edges, without any direction, and without any loop. So when we are talking about the Cayley graph here, means that we have a group G. Of course, we may assume that finite group. In definition, you don't need to assume finite, but we assume finite group because we are going to draw a graph. If you want to draw a graph, so if the vertex are infinite, so it's not possible to draw a graph. So I assume that the group is finite, and we have these two conditions for subset S. Now, by these conditions, we can define a graph, Cayley graph, with the vertex set consists of all elements of the group G. So the vertex set is the group G, right? The set of all elements of G. And if you take two elements, X and Y, in G, if we have this condition, X, Y inverse is in S, it means that X is adjacent to Y. No. Why we don't have any loop and any multiple edges, any direction by these two conditions? You can see that if we have a loop, so it means that X times X inverse must be in S. But X inverse is the identity. We remove identity. So it means that any vertex cannot be adjacent to itself. So we don't have any loop. And also, could you next page? And also, you know that if X is adjacent to Y, so by our definition, X, Y inverse is in S. But you know that we assume that S inverse is subset of S. So inverse of any elements inside of S, again, is in S. So the inverse of X, Y inverse is in S. But what's the X, Y inverse inverse? Is Y X inverse. So it means that Y is adjacent to X. So we don't have any edge. If X is adjacent to Y, so certainly Y is adjacent to X. So it means that we don't have any edge. Let me give a simple example. Most of you know about the symmetric group. If you take a symmetric group, S3, so we have 6 elements, right? That's the permutation. If 1, 2 means 1 goes to 2, 2, 2, 1, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. We have 6 elements in symmetric group S3. If you put S, it's a single set consisting of the transposition 1, 2. Do we have these two conditions which I mentioned for subset S? Well, the first condition is obviously true because it has not contain identity elements. How about the inverse? If you look at 1, 2, what's the inverse of 1, 2? Is again 1, 2, and 1 is inside of S. So we have these two conditions. Now, how about the graph? If you see that you have to check any two elements with the property that X, Y inverse is in S or not. So if you take 1, 2, and identity, so 1, 2 times inverse of identity. So inverse of identity is identity 1, 2, and 1, 2 is in S. So it means that we have an edge between 1, 2, and identity. How about 1, 2, and 1, 2? We don't have a loop because 1, 2 times 1, 2 inverse is identity, and identity is not in S. How about 1, 2, 1, 3? So 1, 2, 1, 3 inverse. The inverse of 1, 3 is 1, 3. So it's 1, 2, 1, 3. If you find multiplication of 1, 2, and 1, 3, is 132. But 132 is not inside of S because S consists only a singleton set is consists only of 1, 2. So it means that we don't have H between 1, 2, and 1, 3. And you have to check, and the graph is the next page. So this is the graph. So we have three ages only. So we have H between identity and 1, 2, 1, 3, and 1, 3, 2, and 2, 3, and 1, 2, 3. Right? So we can denote this graph by 3K2. K2 is a complement. K2 means an H. K1 is single, is an isolated vertex. K2 is an H. K3 is a triangle. K4 is a square with diagonals, right? So it's 3K2. K2 means K2 union of K2 union of K2. Let me give another example. If you take, again, S3 as a group, now we change S by this subset. S consists of 1, 2, 1, 2, 3, 1, 3, 2. So we have two conditions for S, because S does not have identity elements, and also the inverse of any elements are inside of S. The inverse of 1, 2 is 1, 2, which belongs to S. The inverse of 1, 2, 3 is 1, 3, 2, and its inverse. And similarly, 1, 3, 3, 1, 3, 2 inverse is 1, 2, 3. Now, how about the graph? You know, the graph is a little bit bigger than this, have more edges. You know, this graph, because we have 1, 2, so it means that all edges which we had for S equal to the singleton set 1, 2, tell us something else, right? So we have edge between identity and 1, 2. Here we have edge between identity and 2, and plus some other edges. Next page, please. So what's the biggest size of S? If you take a group G, the biggest size of S is that if we remove identity from a group. If we remove identity from a group, is the biggest possible case for subset S, right? In this case, if you take S, it's the whole group minus identity, then you will get complete graph, because you will have H between, because if you take any two elements, X, Y inverse is an element in group G. And if X is different to Y, it means that X, Y inverse cannot be identity. So we have H between any of two elements. So in this case, the K graph is K6, because we have 6 elements. We have symmetric group of order 6. We have some basic results for K graph. You know, the first one, which I mentioned as above, if you take S as the group G without identity, then the graph is complete graph. The second property of a K graph is that the K graph is always regular. Now, what's the regularity, right? Next page, please. So, the regularity of K graph is exactly the size of S. So if you take any element, any vertex in K graph, the degree of any vertex is the size of S. You remember that in the first example, I considered S as a singleton set. So the size of S is 1. So we have 3 edges. What the degree of any vertex is 1. For the second example, we had S consists of 3 elements. So the degree of any vertex is 3. For the last one, which is the K6, we have 5. The size of S is 5 because we remove identity, right? So the degree of any vertex is 5, and that one, if we have the degree of any vertex is 5 in a graph with 6 vertices, is a complete graph. K6, right? So this is the example, and you know that the connectivity of K graph is important and is related to subset S. Is subset F is a generating set. Generating set means that if we can produce, if we can generate all elements of group S3 by subset S, or equivalently, if S is a generating set, then we have a connectivity for K graph, right? So the graph is connected if and only if S is a generating set. And also, if we have an automorphism, you know, this is automorphism for a group. If we have automorphism for a group, then we can say that we have isomorphism between two K graphs. You know, this is automorphism between two graphs. Automorphism between isomorphism between two graphs is different to isomorphism between two groups. For isomorphism two graphs, what we need to have a bijection between two set of vertices between two graphs, and also we have to preserve edges. So if you have edge between X and Y, the image of X and Y, you should also have an edge between F of X and F of Y, and converse. But the property number 5 is that we may have some kind of automorphism in K graph. So if you have this map for any element, any fixed element G, if you take the map rho sub G with this rule, take any element X to X times G. So this map is automorphism of K graph, right? So by this definition, we may also see that the K graph is almost vertex transitive. Vertex transitive means that if you take any two vertices, if we have at least one automorphism taking the first vertex to the second vertex, it means that the graph is vertex transitive. And this property actually satisfying for the K graph. Now, here is some until now I just defined the K graph. You can see the definition of K graph in many books. In any graph theory books, you can see the definition of K graph. Now, here is some new algebraic graphs coming from K graph. So what I am going to mention from now to the end is to introduce some new some new algebraic graph. Maybe some of them are a special case of K graph, or maybe some different to K graph, generalization or something like similar to K graph. Now, the first graph which I want to introduce here, I give the name prime order K graph. So what's the prime order K graph? We have a group G as we had in K, right? And we have a subset S. But I consider S in a special subset.
چیه؟
Question? Any question? Okay, so I'm just considering a special subset for a group. What's a special subset? If you take element subset S as the set of all elements X, with the order of X is prime, you know that if we have a symmetric group, so if you consider elements in a symmetric group, the elements of symmetric group, because we have two prime numbers dividing the order of S3. So order of S3 is 6. We have two prime numbers, 2 and 3. So F consists of all elements having order 2 or 3. If we have a group of order 12, So we may have some kind of vertices, some kind of elements from by order 2 or order 5 or order 4 or order 6, right? Or order 12. So S consists of all elements of order 2 and 3 because 12 is 2 to the 2 squared times 3. So S consists of all elements of the group G with prime order, right? So in this case, because if you take K graph with different subsets, so you will have different K graph. In this case, with this special subset, we call prime order K graph, right? Okay, let me give an example. Next page, please. So, as I mentioned, if you look S3, we have 6 edges, so that's the order of elements, you know, except identity, right? So, of course, you may also consider not identity because we remove identities because S we have conditions, you know, for K graph. So S consists of all elements of order P. So identity cannot be inside of S. So if you take this graph, so the S consists of 1, 2 as order 2. So we have 1, 2 inside of S. 1, 3, and 2, 3. These 3 elements have order 2. And also 1, 2, 3, 1, 3, 2, they have order 3. So S consists of all elements except identity. So what's the graph? It's K6, it's a complete graph, right? Now, if you take Z6, cyclic group of order 6, so we have 6 elements, right? So the order of 0 is 1. The identity order of 1 is 6. So you have to add 1 6 times to have 0 because 0 is equal to 6 or multiplication of 6. Order of 2 is 3. Order of 3 is 2. Order of 4 is 3. And order of 5 is 6. So what the elements of subset S? S consists of all elements of order because if you look Z6 as order 6, we have only 2 prime numbers dividing the order of 6. So all elements of order 2 or 3 can be inside of S. So S consists of all elements of order 2 or 3. So it means that S consists of 2, 3, and 4. Now, what's the graph? The graph is triregular because S has size 3. So you can see that this is a graph for the K graph. Now, let me give some basic results for the prime order K graph. If you take the direct product of cyclic groups of prime order, like this, G is a cyclic group of order P to the n minus 1 and P to the n minus 2, you know, we consider only P. And P to the n minus, and P to the n sub T. So the first thing is that what's the size of S? How many elements of order P we have in group G? If you compute the number of elements of order P, which is the size of S, is P to the T minus 1. And you know that the K graph is size of S regular. So the K graph, the prime order K graph is P to the T minus 1 regular. Now, we can see that the structure of this graph is the union of some components. You know, the graph is not connected, so we have some component, but each component is a complete graph of size P to the T. It's interesting to see that when the Cayley graph of cyclic group of prime order is planar. What's the meaning of planar? Any of you know about the planar? No? Planar means that if we have a graph, if we have not this situation, two vertex contact together, right? If we don't have this situation, then the graph is planar. So sometimes you may have a graph like this. Look at K4. Is that K4 is planar or not? So what you say, Azir? Planar or not?
Yes.
Planar? So is planar or not?
Yes, planar.
Why is planar?
No edges intersect.
Yeah. You know, if you look this one, these two edges had intersection. So if you can see, you can say at the beginning that it's not planar. But if you draw this edge here, now, do we have any intersection between any two edges? No, so the graph is planar. So the planar means that you have to see that if the first version of the graph is not planar, if you can able to draw the graph with the same condition in some other ways to have this situation, then the graph is planar. But sometimes you cannot do this. For example, if you have a complete graph K5, you know, even you remove this edge and put other side, even you can remove this edge from this one. So what we can say about this is not possible, right? So it means that there is no way to find a graph without any intersection. So it means that the K4 is planar, but K5 is not planar, right? Now, for the graph which I mentioned about the cyclic group of prime orders, you know, direct product of prime orders. So the only Cayley graph has one of these, the cyclic group of order 2 to the n-1, and direct product of two cyclic group of 2 to the n1 times to the n2 and z3. That's the only three groups which we have prime Cayley graph, which is planar. We can compute about the Killick number, about the chromatic number, about the independence number, about the energy, and about the dominating numbers. We don't have to explain each of them. So there are some basic things. Explain to this. Now, I'm going to assess some research problems for all of you here or online participants. You can deal with this some sort of questions. So what's the structure of prime order Cayley graph for symmetric group? I consider only for S3. What we can say about S4, S5, or general in S10? It's very interesting to find this. But even, I'm sure that it will be a good paper to publish. Now, the second question, how about the prime Cayley graph of dihedral group of order 2 times n? You know, dihedral group much easier than to symmetric group. You know the definition of dihedral group of order, for example, 8, of order 10, 12, right? So what's this? And also what we can say about the quaternion, generalized quaternion group. So you know the definition, so you don't need to mention what the definition. You can follow definition of this sort of groups in group theory books. Now, we can also compute some topological indexes. We have some topological indexes in graph theory. You can see we have many topological indexes. We have the Zagreb index, we have Wiener index, we have many topological indexes. So the other research problem is to find some of these topological indexes. And also, we have some matrices for a graph. For example, we have adjacency matrix, we have Laplacian matrix, we have signless Laplacian matrix. We have many matrices associated to a graph. So what's the matrices? So you can find matrices for some of these graphs. And also, if you find the matrix, you can find the eigenvalues of these matrices. The sum of absolute values of all eigenvalues, we can name energy of a graph. So we may find some kind of energies for this graph. Right. The second Cayley graph is against of the previous one. You know, the prime order Cayley graph, the subset S consists of all elements of prime order. But here, if we consider all elements of group G with composite order means that we should have at least two prime numbers dividing the order of that elements. For example, if you take Z4, so we have 4 elements, right? The elements we have 1, 4, 2, and 4, the order of these elements. So if you take 1, is 4. So the order of is composite number means that it should have it cannot be prime order. You make just opposite of prime order. So S consists of 1 and 3, cannot be 2 because 2 has order 2, right? So the graph is a cycle of length 4. And similarly for Z5, you know, if you get Z5, the order of each element except identity has 5. So do we have any elements with composite order? No, they are all order of order 5. So the S is empty, and the Cayley graph consists of 5 isolated vertices, right? Now, the third one of the graph is that if we assume that the subset S consists of all elements of a square of prime order, so it is the order of X must be P squared, exactly P squared. So if we have a group of order, for example, the next page please. You know, so if you take a group G, so we have some prime numbers dividing the order of G. If P1, P2, and Pk are all prime numbers dividing the order of G, so here S consists of all elements having of order P1 square or P2 square or Pk square, right? So for example, if you have a group of order 36, so we have 2 square times 3 square. So the order of 2 square and 3 square are in subset S. So this graph, I give the name prime a square KD graph. The previous one was prime KD graph, a prime square KD graph, right? So if you take this group of order 36, so you can see that we have 36 elements, and we can find S. So we divide S in two subsets. S1, the elements of group G has order 2 to the 2 square, which is 2 elements, x9 and x to the 27, and the next page. And S2 consists of all elements of order 3 square. So we have some elements here. So S1 union to S2 is a subset S, consists of all elements. 2 minutes, really. So this is a graph which we can just mention the same research problems for this graph, right? For P square KD graph. So I mentioned to determine the KD graph, prime order KD graph for symmetric group. Now, how about the prime square KD graph? I mentioned about the prime order KD graph of dihedral group. What we can say about the prime square KD graph? So there are many questions about the KD. Now, in the few minutes, just to stop here. In the few minutes, I just want to give some new ideas. If we replace P squared by P cubed, you may give the name prime cube KD graph, right? It's the new graph. But you can see that if we are talking about prime square KD graph or prime cube KD graph, so we must have prime, that prime order divided the order of G. Because if you take S3 has some elements of order 2 or 3. We don't have any elements of 2 squared, which is 4, or 3 squared. So in this case, S is empty. Figure out concept of some undirected. As for groups of bigger orders, right? You can define about this. So this is a new idea about the KD graph. From definition of KD graph, I will introduce 2 graphs, and you may continue for some other graphs. Of course, I had something to say, but the time is not enough. Maybe in the future, or some other times, to introduce some of new attributes. Thank you very much.
Thank you very much, Professor Ahmad, for your presentation. It's such an insightful topic that you gave us. And I hope all participants can have some inspiration and also motivation for our future research from your speech today. Okay, sadly, we can have the Q&A question since the time is, yeah, run out. Okay, so once again, thank you for coming here and sharing with us. Please, all participants, give a round of applause for Professor Ahmad. Okay, so before we close this seminar, we would like to invite all participants to have a photo session with our speakers today. Okay, so if you would please all come in front of the room. And for all the participants in Zoom, if you would please open your camera for a minute. Okay, please, all participants in the room. Okay, thank you, everyone.
Thank you, Bro Ahmad.
Okay, by the end of this photo session, the seminar will also has also ends for today. And thank you for coming here, and we'll see you again in our next seminar. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.